Hello. Proof tends to be one of the hardest subjects in geometry to master. And we're going to do a little bit of a proof. This is an algebraic proof, so it's going to use algebraic rules like the addition, subtraction, multiplication, or division properties of equality. Also included in this list are things like the reflexive property of equality, where something is equal to itself, or the symmetric property of equality, where you can reverse the order and say if 5 equals A, then A equals 5. Okay, so knowing these rules is kind of important. And really it comes down to just those 6 properties. In reality, 5. The addition, subtraction, multiplication, and division properties of equality that all allow us to do the same thing to the opposite sides of an equation, and the symmetric property, which allows me to flip an equation and say if 7 equals A, then A equals 7. Let me demonstrate with this problem. If 12 equals 2 times the quantity x minus 7 plus 6, prove that x equals 10. Remember the way a proof works. A couple of things to remember about proof. One, we start with what we're given. We start with the given. In this case, what is given is the equation 12 equals 2 times x minus 7 plus 6. Second, we end with what we're trying to prove. We end with x equals 10. If you haven't started with what you're given and you haven't ended with what you're trying to prove, chances are you probably haven't done the proof correctly. Okay. The third principle of proof is that every statement must be justified with a reason. And we don't just say, I added 5 to both sides. We don't just say what we did. We cite the rule that allows us to do what we did. So let me demonstrate. So the 12x, or 12 equals 2 times x minus 7 plus 6 is known as the given. And the x equals 10 is known as what we're trying to prove. You may recognize the given as what we call in a conditional statement the hypothesis, and the prove as the conclusion. Okay, in fact, if we were proving a conditional statement, that's exactly what we're doing. We're given the hypothesis, we're proving that the conclusion must follow. Okay, so we're going to start with the given. So the very first line, I'm going to do a 2-column proof. So we're going to have statement. Okay. And we're going to have rules or reasons. I prefer rules because it's more descriptive. Okay, rules say who gave you permission to do this? What theorem, what rule says you can do this? That's really what we're citing. Statement 1 is going to be the given statement. 12 equals 2 times the quantity x minus 7 plus 6. Okay, rules say, how do you know? How do you know 12 equals 2 times the quantity x minus 7 plus 6? The answer to that is, well, it was given. I was told it was true. Okay? And there must be some points in any proof that we assume the given is true. Okay? That's an if-then statement. So if the hypothesis is true, all of this hinges on whether or not 12 equals 2 times x minus 7 plus 6. But if that is true, we will conclude that means x equals 10. So the very last statement of my proof is what I'm trying to prove, x equals 10. Now I see this a lot. I see people put prove down as the reason or the rule. How do I know x equals 10? Prove. Well, that doesn't make sense. And it doesn't make sense because it's actually incorrect. There is no justification, no rule called prove. So prove, the word prove, should never appear as a reason or a rule or a justification in your proof. Okay? Or proven or proof. Any of those. Okay? All right, so I know the last step is going to be x equals 10. So it starts with the given. It ends with what I'm trying to prove, and the rest of the body of the proof is what fills in the steps in between. Okay? Now I'm going to use a little bit of algebra. I'm going to write in white some things that normally would not appear in the proof. All right? You know from your rules of algebra that we start from the outside and work our way in, that we do opposites to get rid of things, and so on and so forth. So I'd like to get rid of the plus 6. The opposite or inverse of plus 6 is minus 6, and algebra has taught us that if I subtract 6 from the right side of the equal sign, I subtract 6 from the left side of the equal sign. All of that's well and good, but that's not really what happens in a proof. In a proof, we simply state that 6 equals 2 times the quantity x minus 7. Okay? And we say what rule says that 6 equals 2 times the quantity x minus 7. And the rule that gives me permission to subtract 6 from both sides is the subtraction property of equality. Subtraction property of equality. Okay? And that says I can subtract the same thing from both sides. Note this is not the addition property of equality. That's the most common wrong answer here. We're not calling it the addition property because there was a plus 6. We're calling it the subtraction property because we actually subtracted 6 from both sides. And the rule that allows me to do that is the subtraction property of equality. Let's go on. Peeling the onion. We know that we need to get rid of the 2 by doing the opposite or inverse of multiply 2. So I'm going to divide both sides by 2. And again, what I'm writing in white typically is not written. Okay, but I'm just writing it so it's clear what's going on. 6 divided by 2 is 3. 2 divided by 2 is 1. 1 times x minus 7 is x minus 7. What rule allowed me to divide both sides by 2? That rule is the division property of equality. Division property of equality. Okay, so again, note I'm not saying what we did. I'm not saying we divided both sides by 2. In a proof, the rule is the reason that justifies, that says I can do what I did. Okay, we're not stating what we did. We're stating the rule that says we can do what we did. By the division property of equality, dividing 2 from both sides, 3 equals x minus 7. Okay, and finally, I'm going to eliminate the takeaway 7 by adding 7 to both sides. Okay, and lo and behold, 3 plus 7 is 10. So I'm ready now to bring in my last step that I knew I was going to get to. Oh, no, I'm not ready to bring in my last step. There's one more step, and I'll explain here momentarily. Okay, so by subtracting or adding 7 to both sides, I end up with 10 equals x. Okay, and step 4 said we got that by adding x 7 to both sides. So we use the addition property of equality. Addition property of equality. Okay, now we do have one more step. Okay, this is not x equals 10 like I wanted. This is 10 equals x. And you might be tempted to think, well, I'm done. I've proven what I set out to prove. Technically, no. You're not done proving until you end up with the exact statement that you set out to prove. We set out to prove that x equals 10, not 10 equals x. And you might argue, well, it's obvious that they both mean the same thing. Well, that's not entirely obvious. And unfortunately, it's obvious is never a reason in a proof. Okay? Well, obviously, right? You're not going to win any arguments by stating, well, that's obvious. Unfortunately. So we're going to put in one last step, right? And we're going to say step 5. X equals 10. X equals 10. Statement 5. What rule allows me to say if 10 equals x, that x equals 10? What rule allows me to switch them? There is a rule that allows that. And that is exactly what the symmetric property is for. By the symmetric property of equality, which says I can switch the order, x equals 10. And we did finally set out to prove what we set out to prove, so I can end my proof with QED, quod erat demonstrandum. Which is Latin for I said it, ergo, therefore I proved it, or I demonstrated it. All right, so that's an algebraic proof. Hopefully that makes sense.